Okay, so welcome back, and now what we're going to talk about is hypothesis testing involving two populations where we want to compare population proportions instead of population means. So we're going to look at the difference in proportions instead of the differences in the population means. So in this case here, again, our hypotheses are going to change only in that we're going to use P1 and P2 instead of mu1 and mu2. Okay? So our assumption is always going to be the null, which is going to be that there is no difference between P1 and P2, okay, or the population proportions. So now a couple of things that I want to cover is that we want to make sure that all the conditions are met. Okay, so just like we were talking about with the means, let's talk about the population proportions. Okay, so some of the assumptions that we're going to make is that we're using two independent and random samples, just like before. Okay, so that's one of the assumptions that we're making, that the samples are independent and random. So now, also, we want to make sure that the number of successes and the number of failures are at least 15. Now, some textbooks, again, use 10, I think, but some textbooks use 15 because they believe 10 is too liberal. So we've been using 15. We're going to stick to 15. That'll be fine. I've seen some textbooks use 5. Okay, I think that's too small for these circumstances, but 10 is typical. We're going to use 15, so we'll stick with that. But 10 is usually fine as well. So the thing is, we want to make sure that the number of successes and the number of failures is at least 15 for both samples. Okay. So one of the things we need to make sure is that if we have two populations, so we have population 1 and we have population 2, and now we want to compare P1 to P2. So we need to know the distributions, that the distribution of P hat and the distribution of P hat 1 and P hat 2 are both normally distributed. That's, again, along the same lines that I went with the other one when we were talking about the means. So if I want to know that P hat is normal, P hat 1 is normal, then what do I have to check? I have to check that N1 times P1, right, is greater than or equal to 15, and then N1 times Q1 is also greater than or equal to 15, but also that N1 is greater than or equal to 30, right? And also with the second population, similarly, I want P2 to be normally distributed. So what are the conditions that need to be met there? Same conditions. N2 has to be bigger than or equal to 30. N2 times P2 has to be bigger than or equal to 15. And finally, N2 times Q2 has to be bigger than or equal to 15. Okay? So now, if these conditions are met, then I know that P1 hat is going to have a normal distribution that is what? Has a normal distribution with a mean of P1, right? And a standard deviation of P1, Q1 over N1. Okay? Now, if the second population meets these conditions, then I know that P2 hat is also going to be normally distributed with a mean of P2 and a standard deviation of P2, Q2 over N2, so the square root of that. Now, if all of these conditions are met, and I'm dealing with a two-population hypothesis test, then what I can do is now I'm looking at the differences between these, and I want to know, hey, is the differences between P1 and P2 significant? So I'm going to need to know the distribution of the random variable for this situation, which is going to be, as you might guess, P hat 1 minus P hat 2, or P1 hat minus P2 hat. Okay? So now I need to know the distribution of this. Well, it comes, and again, I'm not going to derive this, but it comes to no surprise that if all of these conditions are met, then I know the distribution of P1 hat is normal, and the distribution of P2 hat is normal. And so if I subtract those two distributions, well, the differences are also going to be normal. And what's the parameters for this normal distribution, as you might guess? Well, the mean of P1 hat minus P2 hat is going to be mu. Oops, I almost said mu. It's going to be P1 minus P2. And as you might also suspect, the standard deviation of this distribution, or the standard error, rather, is going to be what? It's going to be P1 Q1 over N1 plus P2 times Q2 over N2. Quantity squared, or quantity square rooted. So what we're going to get is, if all these conditions are met, all 6 of them are met, then we know that the distribution of P1 hat minus P2 hat is going to be approximately normal with this mean and this standard deviation, which is going to be the sum of the variances, okay, which we've seen before, okay, with confidence intervals. Okay. Now, how does this help us with hypothesis testing involving 2 populations where we want to compare the population proportions? Okay. Well, a couple of things we have to keep in mind. Well, generally, under the null hypothesis, well, what are we doing? We're stating that the population proportions are equal, right? Well, what are we going to do? Are we going to use P1 or are we going to use P2 if they're the same? Well, we don't know what P1 and P2 are, right? Under the null, as you can see, we're assuming that they're the same, right? But we don't know what they are. We're just assuming whether they're the same or different, and under the null, we're going to assume that they're equal. But we don't know what the population parameters are in this case. So what are we going to do? Well, we're going to end up sort of doing what we kind of did with in the case where we were pooling the sample variances, okay, but not quite the same. But it's kind of akin to that, because in that situation we assumed that the population variances were the same. So what did we do? We took the sample standard deviation, or the sample variances, and kind of took an average, sort of speak. So we're going to do this kind of the same thing here. So what we're going to do is, if we're going to assume that the population proportions are the same, we're going to basically take an average of the 2 p hats. And we're going to take that average as the same for both of them. Okay, we're going to replace P1 and P2 with that average. Okay, so how do we do that? The calculation that we're going to use to do that is this. So let me start with this. So here's, again, the calculation for the standard error, or the standard deviation. So P1 Q1 over N1 plus P2 Q2 over N2. Okay, now, since we're assuming under the null, P1 is equal to P2, what we're going to do is, since we don't know what P1 and P2 are anyway, we're going to use P1 hat and P2 hat. And what we're going to do is we're going to calculate a new proportion that we're going to replace both P1 and P2 with. Okay. Now, the textbook uses P sub C, which I believe, what do they use P sub C for? Oh, well, yeah, okay, cool. It's the pooled proportion. So it's the pooled proportion, P sub C. Now, other textbooks I've seen, which we use in this class as well, is P bar, okay? Which is fine, because it's like the average X bar, P bar, so think of it that way as well. But this is kind of like a pooled proportion. So what we're going to do is we're going to add the x's, right? We're going to add the number of successes from sample 1 to the number of successes in sample 2, and then we're going to divide by the combination of both samples. So we're going to do N1 plus N2. And that's what we're going to do for the pooled proportion. Okay? So here's what it says here, just so you guys read. It says, generally, the null hypothesis will state that the two population proportions are the same. That is, that P1 is equal to P2. That's what I noted up here. And since the population proportions are equal, the variances of the individual sampling variations will also be equal. That should make sense, right? Because if these two are equal, obviously the variances are also going to be equal. So that goes without saying. That's why it makes sense to think of this as like a pooled variance type of situation. So we get a better approximation to this common variance by using a pooled proportion, which they call P sub C, or we can call P bar. And so what we do is we add the total of the successes from both samples and divide by the combined sample size for both samples. And so this is what we're going to replace. So what happens? Now I'm going to go back. So what we're going to do is we're going to replace P1 and P2 with P bar. Now also, we're going to have to deal with Q1 and Q2, right? So obviously if this is this, Q bar is going to equal 1 minus P bar. So now what we're going to do is we're going to replace P1, Q1, and P2, Q2 with the same thing, P bar and Q bar. Okay, now you see what's going to happen? We're going to simplify this formula similarly the way we simplified the one with pooled variance. So what we can do is now we can factor out the P bar times Q bar. So what we're going to end up getting is this calculation here. It'll be P bar Q bar times 1 over N1 plus 1 over N2. And that's the standard error that we're going to use for our test. Okay, so now that's what we're going to use. So now this is what we're going to call, so ultimately this is what we're going to call the standard let's see here. Yeah, the standard deviation of the error. So it's standard, the sigma of p hat 1 minus p hat 2. Okay, which again, it just makes sure that we understand what we're putting in. Okay, so here's our test statistic. So now knowing that, here's what our resulting test statistic is going to become for the hypothesis test for the difference of proportions, right? So Z star is going to be this calculation. It's going to be, of course, p hat 1 minus p hat 2 minus p1 minus p2 divided by now the square root of p bar q bar times 1 over n1 plus 1 over n2. And so this now becomes our calculation for our test statistic Z star. Okay. Now, notice also that under the null, this difference is 0. So just like before, it's going to reduce to just this. P1 hat minus P2 hat over the square root of P bar Q bar times 1 over N1 plus 1 over N2. And that's it. Okay? So that's all there is to it. Everything else is going to stay the same. And also, for the calculator, when we do our tests, really, the only test we're going to do in this case for the for two population for proportions is going to be this. It's now going to be 2 prop Z test, right? Last time for the one population situation, it was just 1 prop, 1 proportion Z test. Now it's going to be the 2 proportion Z test. So this is the function. This is the calculator function that we're going to use. Okay. So let's do an example. So in an example, let's see here. Okay, so by the way, when I went to the conditions, by the way, understand that because we're using samples, those conditions, replace P1 and P2 and Q1 and Q2 with P hat 1 and P hat 2. So understand that when we do those conditions, since we don't know what P1 and P2 are, replace those with P hat and P1 hat and P2 hat, and then do your conditions. So always check your conditions to make sure that we've got the normal distribution assumption met. Okay, so anyway, going on. So here's the example. It says 2 types of medication for hives are being tested to determine if there is a difference in the proportion of adult patients' reactions. 20 out of a random sample of 200 adults given the medication still had hives. 30 minutes, excuse me, let me repeat that. 20 out of a random sample of 200 adults given medication, medication A, still had hives 30 minutes after taking the medication. 12 out of another random sample of 200 adults given medication B still had hives 30 minutes after taking the medication. Test the claim that there is a difference in the proportions using a 1% level of significance. Okay, so now the 2 medications, medication A and medication B, are used to relieve patients of hives. So now, the claim is that there is a difference between the two medications as far as the proportion of patients that experience relief after within 30 minutes. Okay, so that's the claim. So let's say medication A, let's say the population on medication A is population 1. So medication A is going to be population 1, and those on medication B will be population 2. And so with the claim being that there is a significant difference between the two proportions, we're going to say that P1, right, is not equal to P2 is the alternative, right? Because they're saying that there is a difference. So this is the claim. Versus P1 is equal to P2, right? That there is no difference, right? But the claim is that there is a difference. So that's not equals. Okay? We don't care which one's different. They're not making a claim about medication A is better than medication B or medication B is better than medication A. All they're saying is, well, we believe that there's a difference between the medications. Okay? So that's why it's not equals. So versus the null, which is definitely has to be equals. Okay? Now, this is a two-tailed test. Step 2 is we're going to assume the null is true. So assume P1 is equal to P2. In other words, again, I'm going to write it this way. Same thing. Okay? Now, step 3 is let's write down the information. Now, alpha in this case is equal to 0.01. They want a 1% level of significance. Okay? Which means they only want a 1% chance of committing a type 1 error. Remember that? Okay. So population, so alpha is 0.01. And what else do they tell us? Well, let's write down our two populations. So A is 1, B is 2. So this is 1, this is 2. So what is the information they give us? So now, 20 out of a random sample of 200 adults who are given A. So that means N1 is equal to 200. And out of the 200, what is the number of people who experienced relief? Well, 20 didn't experience relief. So that means 180 did, which means n minus x is 20, right? That's the 20 that didn't, okay? So this is n times p hat. This is n times q hat, okay? So we need to know that. Now, what about B? N2 is also 200. And of the 200 in that sample, 12 did not experience relief. So that means how many did? Well, 188. Which means then N2 minus X2 is 12, right? So now, let's do our checks. So N1 is bigger than or equal to 30, check. N2 is bigger than or equal to 30, check. The expected number of successes for this sample is definitely bigger than or equal to 15, so that's check. This number is definitely bigger than or equal to 15. Check. The expected number of failures is definitely bigger than or equal to 15. Check. Now here, the expected number of failures is 12, but here's where I'm just going to let you know that this textbook is using 10 as the minimum, not 15. So I'm going to go ahead and check this off as check. But again, we're using 15. A lot of textbooks use 10, but again, I've seen some textbooks use 15, and I guess we're using 15 for this class. So, but anyway, just keep that in mind. So anyway, I'm going to consider all of the conditions satisfied. So now, what do we know? Based on this, we know that p hat 1 minus p hat 2 is normally distributed with a mean of p1 minus p2, which in this case we're assuming is 0, right? And the standard deviation of this is going to be p1 q1 divided by n1 plus p2 q2 divided by n2, and then take the square root of that. And that's the parameters, okay? So again, why do we need to know this? Because if you're going to calculate the t-statistic, we need to know that. And by the way, we also want to calculate p-bar, which in this case, p-bar is what? It's going to be x1 plus x2 divided by n1 plus n2. And so what do we do when we get that? That's 180 plus 188. Well, that's going to be what? 368, right? Yeah. That's going to be 368 divided by 400. Okay, and so what do we get when we do that? So 368 divided by 400 is 0.92. Okay, so this is going to be 0.92 is going to be our p-bar, which means q-bar is going to be equal to 0.08. Okay, so this would be what we would use in our calculations for step 4. So step 4, in calculating our z star, obviously p1 minus p2 is going to be 0. So it's going to be p hat 1 minus p hat 2 divided by the square root of p bar times q bar times 1 over n1 plus 1 over n2, quantity square rooted. So now what I'm going to do is I'm just going to add, I'm just going to plug and chug. So what do I get? Well, what's p hat 1 and p hat 2? We still need to figure that one out too. So p1 hat is equal to x1 over n1, so that's 180 over 200, which is going to be, well, it's going to be 0.09, or excuse me, 0.9. Okay, so it's going to be 180 divided by 200. Yeah, 0.9. Okay, and then p2 hat is going to be 188 over 200, which in this case is going to be 0.94. Okay, so there's my p hat and q hat. So if I do p1 hat minus p2 hatter, then what I'm going to do is I'm going to get 0.9 minus 0.94. So it's going to be 0.9 minus 0.94 over the square root of, well, then it's going to be 0.92, right? So it's going to be 0.92 for p bar times 0.08 for q bar times 1 over 200 plus 1 over 200, which will make things easier to calculate. So now, what do I get? Well, let's calculate this. So it's going to be 0.9 minus 0.94, and I get negative 0.04 for the top. Okay, and then for the bottom, I get .0271. Hold on a second. 0.0271. 0.0271. And so if I take my -0.04 divided by, I get -1.474. Negative 1.474. That's my test statistic. And then once again, at this point, I can go ahead and use my calculator to calculate the p-value, right? So the p-value, because now I can take my z-score, my test statistic, and calculate the p-value. Now it's negative, right? It's a two-tailed test. And this turns out to be negative, so what I'm going to do is I'm going to take the probability that my z star is less than or equal to, since it's negative. So I want to go more negative. So I want to, z star is less than or equal to negative 1.474. Well, then all I have to do is just use Normalcdf, right? And then, so my lower bound here is going to be negative 10 to the 99th power. My upper bound is going to be my statistic, negative 1.474, followed by 0, 1, since it's a standard normal distribution. And so now my p-value, I can just use my calculator. So my p-value is, it's going to be negative 10 to the 99th power, comma, negative 1.474, comma 0, comma 1. And now I get 0.0702. So 0.0702, and now I can do my comparison. And so if I compare my p-value to my alpha level, am I going to reject? The answer is no, because my p-value is not less than alpha, okay? But let's use the calculator function to proportion z test, okay? See if we get the same thing. So we're going to use 2 prop z test. And again, we're just going to fill in the information. It's going to ask you for x1, n1, x2, n2. It's going to ask you for the alternative hypothesis, and that's it. It'll do all the calculations with that information, okay? So again, all you're going to put in there is x1, n1, x2, n2. And then it's going to be the alternative hypothesis, which is not equal to. Oh, and by the way, I just forgot. We calculated the p-value. The p-value is wrong. Remember, I forgot to double the area. I just made the mistake that I warned you guys to. So the p-value was what? The p-value was the probability that I calculated was 0.0702. But wait a minute. Remember what I said? That was the probability of my z star being less than or equal to negative 1.474, right? That's only one tail, right? And I said that and I didn't even follow through with what I said, so I apologize. So let me go back to the p-value. It's a two-tailed test. My z statistic was negative 1.474, and since it's negative, I'm going to go to the left tail. Since it's already in the left tail, I'm going to find the probability of, or the area to the left of my test statistic. And that probability, that area, turned out to be 0.0702. 0.02. Now, that's only one tail. That's area in one tail. So now what I have to do is I have to calculate the p-value, which is going to be equal to 2 times this value, 0.0701. Now, what is the true p-value? It's going to be 0.1402. That is the true p-value. But again, we get the same result. It's still bigger than our alpha level, 0.01. Okay? But I just wanted to make that correction that because it's a two-tailed test, I take the probability of being as extreme or more extreme than what I got, which is this value, 0.0702. But to get the p-value, I have to double it because I have 2 tails. And so I have to double that area. And so the correct p-value is 1402. Okay. Okay, so now let's get back to this. So now, once I put this information in, it's going to give me both my test statistic and my p-value. So let's go ahead and figure out, and let's see if I get the same answer. So I go to tests. I'm going to go all the way down to number 6, which is 2 prop z-test. Now, what is x1? x1 is 180. What is n1? 200. x2 is 188. n2 is also 200. And we're doing not equals. And that's it. And we calculate. And look at that. I get the exact same thing for my z star. It is 1.474. Now the p-value, excuse me, was slightly different. It's 0.1404. So it's not that bad. I'm only two 10,000ths of a decimal off. Okay, not bad. Okay, why? Because, well, we have round off error in ours. The calculator doesn't. So anyway, that's it. That's how we do it. So p-value, now step 4, p-value is equal to 0.1404, which is definitely not less than our alpha value, which is 0.01. So again, our result is that in this case, we fail to reject the null. And so finally, our conclusion, again, go back to the claim. What's the claim? That there is a significant difference between the proportion of people that experience relief on one of the medications is different than the other medication. Okay, so the proportions of people that experience relief on these medications is different. Okay, that's the claim. So if we fail to reject the null, that means that there is not enough evidence to support the alternative, and in this case, the claim. So at an alpha level of 0.01, there is not enough evidence to support the claim that the proportion of adults who experience relief on this medication from hives is different, okay, between the medications. So in other words, does it matter which medication you take? Well, the evidence says no, not really. Doesn't matter which medication you take. You could take medication A or medication B. It's pretty much the same. Okay. Well, that's it, guys. Hold on. Let's do one more. Let's see if there's another example here. Let's do one more example. Let's see what we come up with here. Let's see. Okay, let's do this one. Let's say We have two types of valves that are being tested to determine if there is a difference in the pressure tolerances. In a random sample of 100 brand A valves, 14 cracked under the 4,500 psi. In a random sample of 100 of brand B valves, 19 cracked under the same pressure, 4,500 psi. Using a 5% level of significance, test the claim that there is a difference in the proportion of valves that crack at the 4,500 psi level. Okay, so it's going to be pretty much the exact same thing that we just did. But this time, I'm not going to go through the calculations. Okay, so let's start over. So now the claim is that there's a difference in the proportion of valves that crack under that pressure. So difference means not equals. So it's going to be mu0 is that P1 is equal to P2 versus P1 is not equal to P2. So again, it's a two-tailed test. So now we're going to assume the null. So we're going to assume P1 is equal to P2, or in other words, again, P1 minus P2 is equal to 0. Now, alpha in this case is equal to 0.05. And what do we know? Here we go. So let's decide how we're going to do population 1 and population 2. So let's just do the first one as population 1. So we'll just put 1 here and 2 here. So this is valve A. So valve A is population 1, valve B is population 2. So for the A's, we have N1 is 100. In fact, both sample sizes are the same. So they're both 100. Of the brand A, 14 of the 100 cracked. Which means they failed. So this is going to be the ones that didn't fail. Okay? So the ones that didn't fail was what? 14 cracked, which means 86 didn't. And so the number of failures is 14. So again, by the way, you can switch these numbers. As long as you're consistent, you'll get the same answer. Okay? So now, let's go over here. So what about x1 x2 and n2 minus x2? Now, x2 in this case, well, the number of failed ones in the second one was 19. So 19 failed here. So 19, we had 19 failures. And here, then that means we had 81 that did not fail. Okay? So 81 successes out of 200, or excuse me, 100. Okay. Now, if we do the checks, all of our checks match based on what the textbook. So again, more than 30, more than 30, more than 15, more than 15, more than 15. Now this one's close enough, but again, the textbook uses 10. We're using 15, but again, check. So now everything is met. We've got the distribution we need. We know that P1 hat minus P2 hat is normally distributed. Okay? So now we can go to the step 4, which is to prop Z test. And so now our Z star, our test statistic, is equal to whatever value we get in a minute. So now, go back to the calculator, and we're going to go to stat test, go down to number 6, and now we're going to stick in our values. So x1 is 86, n1 is 100, x2 is 81, n2 is 100, and we're doing not equals, calculate, and now we get a z-score. Our z-star is 0.9 0.052, which means our p-value is going to be equal to, well, close to 32%, because it's close to 1, but our p-value is 0.3408. Close to 0.3408. And of course, if we use the p-value method, p-value is equal to 0.3408. Alpha is equal to 0.05 in this case. And so is p-value less than alpha? No. So we fail to reject the null again. So therefore, we fail to reject the null. And so now the conclusion is the same. We go back to the claim. What's the claim? The alternative, right? That there's a difference in the number of valves that fail under pressure, under that specific pressure, okay? So what do we say? We fail to reject the null, so there is not enough evidence to support the claim that the proportion of valve A, that crack under pressure is different than the proportion of valves of model A or B that crack under pressure. So in other words, there's really no difference in the two valves as far as cracking under that amount of pressure. So it doesn't matter which valve you use, they're going to pretty much have the same failure rate, is what it comes down to, based on the sample data. And that's it, guys. That wraps up Chapter 10. So next time, we're going to start Chapter 11, which is now going to be introducing tests involving the population variance and the population standard deviation. So now we're going to talk about hypothesis testing and confidence intervals involving that. And then also, we're going to talk about a new distribution called the chi-squared distribution, where now we're going to start talking about chi-squared tests for things like independence, goodness of fit, and homogeneity of proportions. And we're going to talk about that next time. So take care, have a good night, and I'll see you next time.